Okay. So I feel like a complete boomer right now. But yeah, there we are. There we are. Okay, cool. Yeah. So, please tell me if it works. I try to start the thing, and it, I don't know. I forgot to press start stream, and now it should work. Okay, so if anyone has seen the post I made, I've developed a couple of new softwares for Bitcoin Cash, which allows you to make really cool smart contracts and stuff like that. And for that, yeah, we've basically got Iguana, which is a new debugger, and that allows you to like really inspect what's going on in the script. And also the Bitcoin Cash crate, which like I've already posted on Twitter. It allows really cool, like a really basically a type-checked way of writing scripts, which people are already very familiar with. Like people, they write stuff in the IDE and then it says, oh yeah, you've got an error here, and they don't have to like debug the whole thing over and over again. My natural tone of voice. But yeah, can I make it even louder? Maybe here. This? Yeah, tell me if it's good. It doesn't seem to be overdriving too much. Cool. Okay, so the first thing we're installing is Rust. For that you need the Visual Studio build tools. Those are a bit like annoying to get on Windows, but you can just download them from Visual Studio. You have to be a bit careful because by default it will just install the whole thing. If you want just the dev tools, then you can install, like go to Visual Studio downloads and then just install build tools. I don't have it in English right now. Okay, it's still in German, thank you. Okay, and if you do that it's like a couple of gigabytes. I've already installed it, but yeah, be sure to check like if you're on Windows 10 to install the Windows 10 SDK. In the meantime, we can install VS Code just somewhere. Yeah, here. Be sure to check Windows 10 SDK. So all of that. But if you click C++ build tools, then by default this should be checked. Okay. Yeah. So I've installed VS Code. ASMR. Okay. And for Rust, they've got like this installer, which guides you pretty easily. Like I think you just have to press enter all the time, and that's it. But if you like once you install that, you have to use this command prompt, because for some reason like Visual Studio is really bad, and that's why you should use Linux or Mac, because they are much easier to deal with here. So to test if it actually works, you can just like go to your users workspace or something, workspace, and then you can press cargo new, and then maybe test. Okay, that cannot be used. Then my So yeah, I created my program, and then if you then by default it's like hello world, and then you can do cargo run, and yeah, then it'll show hello world. And if there's some misconfiguration, it will like show a really long error like linking didn't work and Visual Studio doesn't work. If you're not on Windows, then it should like work fine. Okay, yeah, already developed a bit, but let's start from scratch. So yeah, cd what's it called? Cache numbers. Yeah, let's remove, is it remove directory? Cache numbers. Okay, what the fuck? Yeah, let's just use this tool here. It's called the Explorer. Okay, well. You also need Git installed, but I suppose that's already installed. Node for the front end. Let's install that real quick. And Yarn, which is basically a small tool on top of Node, which makes things a bit easier. All right, yeah, that one installs quickly. So yeah, for Yarn, I recommend using the git bash. Okay, now the last thing we need to install is the Rust Analyzer. Okay, I already installed it here. We can also install beta toml. Rust Analyzer is like, it is really good at displaying errors for Rust, and it works like out of the box without a lot of configuration. Yeah, it seems to not want. Let's close this and remove. Okay, cool. So now that we're here, we can create a new executable with cargo new, and let's do cache numbers transaction once again. And we can open that in VS Code. VS Code. Yeah, and currently this is just a hello world. So if you run that, cargo run. Okay, we have to go to cache numbers directory. Cargo run. Then it'll show hello world. Okay. Yeah. And I think that's it. Yeah, that's all we need. We've got Yarn, we've got Node. Yeah. Yeah, let's also get the Iguana. Should be here. No, here. Pcache Iguana. Just github.com pcache Iguana and go to workspace and cache numbers. Git clone. And let me paste that here. Then we got Iguana, we go in there, and if we've got Yarn probably installed, let's hope, otherwise we might need to oh yeah, we need to go to Iguana UI. Yarn install. Now we should be able to use yarn start. Yeah, okay, it can't find Google Chrome. So if that's the case, you can just change the package JSON and remove like this part here. Then it's like just open it. Wait, it'll open it in the default browser. Yeah, let's just wait, what did I do? Like this. Stuck in Vim hell. So yeah, so if you use yarn start, then it just hosts Iguana, and you can access it from here. But while this is serving, let's set up our project. So we need the Iguana WebSocket, which should be 0.1, and the Bitcoin Cache crate, which also should be 0.1. Okay, so we can see it compiled successfully, and now everything should be working. Ah, somebody sent a donation. Thank you. Okay, let's create a new file where we set up like a small sample script. And we need to declare the file as a module, which we just do with mod, and then script. Oh, let's call it by its proper name. Okay. Create NFT1 script. Yeah, we'll just leave it at that for now, just so we have a name, because later we will create an NFT1 script, but what that is I'll explain later. So for now, this is just like a toying for toying around, for setting up like the environment. So we import Bitcoin Cache script, which is a macro, and we can invoke the macro by oh, another donation. Wow, thank you. 0.02 Bitcoin Cache. That's very nice. Script. Yeah, just script, and there we have to give the struct. It creates a name. So these are all the inputs. What that is, I will explain in a minute, but it shouldn't be like too hard. Oh, and another donation. Well, thank you so much. Yeah, and then we may create NFT1. Like that, and opening and closing brackets. Oh, fn, yeah. So basically what the macro does, it takes a ordinary Rust function and turns it into a like script constructor thing, and it also extracts the required inputs into a struct. So it would create a struct that's called this, and a function that's called this, that just takes a single argument. Like even if we were to add arguments here, then it'll just still use the first one. So this one we can use to parameterize the our script. So can you do a new struct, create NFT1 params. So we got the params and the inputs. So these basically change the source of the script. So for example, if you had a script that can only be redeemed by a certain public key, then the public key would go in here. So we had something like pub key, I don't know. For now, let's leave that empty, just so, and we can add params later. So just we don't get overwhelmed. In Rust, generally, like try to make the simplest thing possible, and then expand outwards from there. So we have the params, and I usually format it like that. And now we can get inputs. Inputs are like, let's call it number 1, which will be an integer. So let's just make a script that adds two numbers. So integer. Here we can take basically two integers. So now we have a script that expects two integers. I mean, that's not very useful. So how about we just add them? Let sum equal. And for that we need the opcodes. Those have to be in scope, so we also have to import those. Yeah, opcode. Yeah, so this is the syntax for importing like a whole bunch of like all the stuff that's in opcode. So we basically import all opcodes. I think we should be able to get auto-completion if we... Yeah, sometimes Rust Analyzer gets stuck and then you can just reload the thing. So currently we get an error. Okay, it's still loading, but we can already start. So now if we just do op add, then it'll immediately tell us I want to get two input names, but it only got a single input name. No, if it works, yeah. And we even got a usage example. So here you can see it expects A and B. So just for fun, let's type A and B here, A and B. And now it'll tell, oh, actually what's on the stack is number 1, which is, yeah, which are these two. So if I were to plug number 1 in here, then it'll complain about the second one, because here it expects number 2. Now this might be a bit confusing, because like what's the stack and what does it expect, and like what are we doing here? But once we start the debugger, then it'll be more clear. So, and finally we need a signatory. Signatory is a term I started to use. Now we get full auto-completion. Yeah, signatory. And this basically, like your contract has to get signed. And sometimes, like for the stuff I'm doing, it can get really complicated, the stuff you want to sign. Signatory. So for that, I made it like really powerful to create basically all combinations of signatures that depend on the outputs and whatever, like a large Codium, VS Codium. Never heard that. But yeah. Okay. So for that we need to implement signatory, and the keyword is just impl. So impl for create NFT signatory. Yeah. And if we save that, it'll tell us, oh, we actually need a couple of stuff here, and we'll just implement all missing members. So now this is a bit much, but the first thing here is the script that will be produced. So basically the result of the signatory. So when you create a bunch of signatures, then you will assemble that into an input script. So here this will be like all the inputs. So here it'll be just 2 integers. But luckily the script macro just creates the struct for us. Like we can just plug that in here and it'll work. So signatures, so for now we won't use any signatures. So usually you would have maybe a tuple of a couple of signatures, or you make an enum if you expect different signatures for different things. But for now this will just be like empty, which is like the unit type here. Okay, we need to import that. Sig hash flags. Yeah, okay, and it compiles, but we got this unimplemented error, which of course isn't Nice. Where did my bracket go? What? I'm not used to developing on Windows, but this is the fastest machine I got. And first, I deleted it. Okay, I'm a boomer. So here we can specify the Zcash flags. I mean, that's a very technical thing, but it basically says if all of the inputs are signed, or if just a single input is signed, or even if no input at all is signed, and that, well, like, yeah, just a single input. But that's like signing stuff, and it gets a bit complicated. Oh wait, so the placeholder signatures is like, okay, I want to compute the leftover, but like the change back to the sender, back to sender. And to calculate the change, you need to know the size of the transaction. And for that, I basically have to know beforehand how large the input script will be. And for that, the simplest way is just to instantiate like dummy signatures. So for example, these could be signatures that instead of a real signature, just have all zeros. But for here, it'll just be like this thing here, like no signatures at all for now. Later, we definitely have to add at least one signature. I think we'll need exactly one signature. Okay, so we don't need any of that. So to silence it, we can just add a underscore. And then we create this input struct here, which is self : script, which is this one here. So this is Rust notation. So if we save, we see, it's missing fields num1 and num2, which are the fields generated here. So this is a really convenient way of plugging together your script. So for now, let's say this is the number 5 and number 2 is the number 11 or something. And that should compile. Yeah, we just have unused variable here, but that's fine. So now we've created a script function. We can call that, and we've got a signatory which basically creates a input script for a given script. Like for this script, it'll figure out what stuff can be in here. And we can access all these things here, like we can get the outputs of the whole transaction, we can get the log script, we can get like the signatures, and the whole transaction, but without the signatures, of course, and the pre-images. So some of that overlaps, so this is a superset of this, but it's much more convenient to use it like that again, because that you actually use quite a lot, and that not really, but it's in there for completeness. Okay, so let's create an actual transaction with that. For that, we directly use the WebSocket. So this will basically create whenever the transaction is ready, it'll notify the front end, and it makes it really convenient to use. So we use Iguana WebSocket and run Iguana WebSocket. And there we already got a fitting name, make transaction. So this basically just makes a transaction. Let me which this was. So yeah, like this. Any questions in there? Hello everyone. Yeah, if you got any questions, definitely feel free to ask. I'll gladly answer them. So yeah, for that we'll use the transaction builder by the Bitcoin Cash crate. Where is it? Builder, transaction builder, and we probably need a handful of other things, but I think we also need what's it called? Unsigned transaction input. And yeah, let's see what we need. So we'll create a mutable transaction builder. Here we can specify, like, this one is more detailed, but simple, just It's a default transaction builder. So for here, yeah, we've got all these functions that help us to build a transaction, but we'll just make a transaction with a single input and no output for now to keep it simple. So an input, it returns a, can we see it here? It returns a, what's it called? An input reference. So input reference. And that basically allows us to be like, okay, later we can do basically unimplemented to silence this. Yeah, so we have to define the other stuff, but later we can do, we can build, whoops, not box. Nope, that was the wrong. Control C, we can build the whole thing, and we get a unsigned transaction. So this doesn't have any signatures yet, and this might fail because not insufficient funds and so forth. So we have to use the question mark operator to bail. And then this unsigned transaction, this has to be mutable. We can sign each individual input with this reference. So here, okay, it's called token here, but it's input reference. And yeah, signatures are again empty. And once we got that, we can complete the transaction and we get like a finished transaction. It's just not yet hashed, but that that gets handled by Iguana. So transaction, unhashed transaction. Yeah, and I mean, it doesn't work yet, but that's how it works. So to get an input, these are the things we need. So we need an input, which is an unsigned transaction input actually. The log script, which we get from here, which is basically calling this thing. And an input script builder. These are, like, I've renamed them to signatories, but it's still called script builder here, so I have to rename that eventually. Yeah. So unsigned transaction input. Oh, god damn it. So unsigned transaction builder. And the log script is just this function here. Here we need to specify the params, yeah, which we can do just in place. Yeah, note that these other two parameters, they are displayed, but they are actually removed. So these are filled in by the signatory, by this thing here. So this function actually just takes a single input. So create an FT script and the params. Yeah, which here are just empty, so we can leave it at that. So the last thing is the script builder, which is actually the signatory. Create an FT script, which is also empty as far as I know. Why? Okay, keep smashing the wrong buttons. This. Why Rust over Python? So Rust allows me to run an WebAssembly, which allows me, I mean, I can compile Rust to many different targets, which is very important for like being compatible. So for example, I can run, once this is finished, we can just create a different library, and we can do that later. So it can run on like Android. It can also run on, like this is the identical code, like all of that. It can run on Android, it can run on iOS, it can run in the browser with WebAssembly, it can run natively, and yeah, it can run basically everywhere and just with one code base. And that's not possible with Python, at least not if you do like crazy stuff. But with Rust, it's like very, very easy. Okay, not very, very easy, it's easy. It's not the simplest thing in the world. So, Rust is more efficient. Honestly, I'm happy to see any BCH tools that aren't JavaScript. This is I definitely agree with that. But yeah, okay, yeah. Let's continue here. Let me see if that's sehr gute Verbindung. Okay, that's very good. So here we also need the out point. So like this actually creates the full transaction, but like we don't really care about like what's the actual out point. So we'll just put some dummy data in here, and it'll be fine. So yeah, I use special structs for the hashes. So every single hashing algorithm has their own struct, which makes it like a bit more secure. So everything in this crate is about, okay, type checking. So I wanted to be sure that it typed like it's like if there's a bug, it doesn't the compiler picks it up as early as possible, and you don't like run into problems really late. And if you mix up hashes, then that'll, I mean, if you switch SHA double with SHA single, then it'll be hard to spot. All right, so we'll just put the number 12 32 times as a transaction out point, and the out of 0 or something, I don't care. So this obviously doesn't exist, but the debugger doesn't check this, and rightfully so, because it makes it much easier to develop if you can spend non-existing inputs, because you don't waste any money. So we'll do this. Oop. Yeah, the underscore is just a separator. It doesn't really mean anything. Yeah, no new messages. Cool. I think that's it. Yeah, we just get a warning, probably that the name is unused, but that's fine. Okay, that's perfect. So now we got a transaction server, transaction WebSocket server, and that's it. Like now we can debug the thing. Cargo run. Yeah, you can. Let's. There's a thing called watch exec, which you can install that. Oh, a new donation. Thank you. Watch exec. I think it should already be installed. Yeah, it's already installed. It takes a long time to install for some reason, but that's fine. So we can do watch exec, and then it'll like restart the server every time we change this thing. So, but I forgot the command line parameters. I think it's R, yeah, restart, and then we can use something S, sig term, so it'll just terminate the thing. And it'll run cargo run, I think. Is that correct? Yeah, so now it'll compile the whole thing, which will take a while. Yeah, in the meantime, I can check number of we already got a couple of donations. Thanks so much, by the way. Here they are. Cool. That's really helpful. Yeah. Okay, it's still compiling. Yeah, this one warning, but I mean we could silence that. It's not really helpful. Yeah. So now it's serving our WebSocket at 3030. So this maybe doesn't make too much sense, but once I'll show you it, then it should be maybe more clear. So let's just add an empty line here and see if it recompiles. Yeah, it's recompiling. It takes a little. Okay, it takes maybe 5 seconds, which isn't too fast, but I mean, it's one of the downsides of Rust. It takes like a couple of seconds to compile. But now we can check if it's the Iguana UI is still running. So we can just run the localhost, and now it sees transaction updated. So this is actually the transaction hash of the transaction we got here. Let me close that. And yeah, here it should show a overview, but it's I don't feel like that yet. So later maybe someone could add an overview. So yeah, for example, if we change the number here to 12, then it'll restart the server. Let's wait a couple of seconds, and then it'll get a new transaction, and it'll have a new transaction hash, and yeah, and you don't need to, like, you just need to save, which is pretty cool. So now we can have that one here and that one here, and each time we change something, it'll automatically update the stack. Yeah, change. Oh, do we need to do crappy stuff? Okay. Oh yeah, I changed this number, not this number. Let me see that again, if it actually updates. Number 9. Compiling. Yeah, and number 9. Okay, cool. So, but what does all of this mean? So, this is the debugger. This is the main view. And here we've got a couple of columns. So this column just counts up incrementally. This column here displays the source code it's running. So this is the actual source code that's in here, just formatted. Where is it? Here. So if it runs over, it'll shrink it. This is the number of bytes used. So an op-add just uses a single byte. If you push some data, this could be higher. And this is the number of operations performed. So if this number goes over 201, then your script will be invalid. So be sure that this remains under 201. And this here is limited to 520. But you can do some tricks to like get that number really, really far down, which I usually use like straight off the bat. Oh no, wait. No, you can. Yeah, but yeah, you can. You can push that number pretty far down if you do some tricks. But this number is basically like you're doomed. If you run into 201, you need to do like insane stuff to work around that. Maybe do looping transactions or something. So this is the hard limit, so to speak. Okay. So, but we still don't know what is happening here. So the first line is the first operation, and that is basically the starting point of our transaction. So here we got all inputs on the stack. So the stack it can be numbers, it can be booleans, it can be byte arrays. Script actually, like in script, everything is a byte array. It just encodes, like an empty byte array is a boolean false, and so forth. Like a non-empty byte array is a true value, and that and a number is very weirdly encoded. like it's very weird how numbers are encoded in script. But for but you don't have to deal with any of this. This is all handled by the Bitcoin Cash crate. It's just internal logic. So for us, there are only numbers, byte arrays, and booleans. Yeah, and when this function starts, it starts with all the parameters pushed onto the stack. So what's the stack? The stack is basically, yeah, we can add in a couple of more things here. Let's do demo 2, 3. So this will push. Oh yeah, we need new demo values. Oops. So this will push 5 values in total. So let's put that here. 0, 1, and 2. Yeah, this will compile and it'll update it shortly here. Yeah. So now we got these initial numbers on the stack. So we got the number 0, number 1, number 2, and then 9, and then 11. And now this is basically what we can deal with. So this is what we can work with. It gets pretty complicated once you like really think about how to operate, because usually you can only work with the first stack item or with the first and the second stack item. So if I would want to subtract number 1 from number 2, then they would have to be in the right order from the start. So they can't, I can't just run sub right off the bat. I have to change the order of the stack items. So yeah, if I want to subtract number, let's call it, let's give it a more meaningful name. So we've got the wallet, it's a payment amount, for example. This is just an example, and we got the wallet value. So this is the number of Satoshis in the wallet, and this is the amount that will be paid. I mean, that's not very meaningful, but this is how we could use it. Yeah, and if that's the way we get stuff in, and we then want to subtract, then we want the wallet value first and the payment amount second. So it would be the remaining value. Then we obviously get an error, because this says I expect payment amount first and then wallet value. I mean, basically it says this stack item should be payment amount, not wallet value. But that can be resolved easily by just swapping the top 2 stack items. So the payment amount and the wallet value, we can swap those, and now it, like this part at least, compiles. But he obviously expects different things. And expects payment amount and wallet value. So let's get those. Oops. Oh boy, that wasn't good. Okay, and save, and it should update it automatically. Yeah, there we go. So we start with payment amount and wallet value, but you actually want them in different order, so we just swap them around. So wallet value and payment amount. So yeah, let me show another feature of Iguana, which is really cool, which is that it keeps track of all pre-images of the stack items. So let's say instead of like subtracting them. I just want to turn them into a string, into a byte array, and concatenate them, and then hash it with some hashing algorithm like SHA. Yeah, for that we need to turn these values into strings, into byte arrays, and for that, yeah, let's just like encode it. Payment amount. I usually use little endian to indicate that it's encoded, and sometimes I put like a 4 here, so it means like 4 bytes, little endian, and I can use op num to bin like this, where if I save that, then it'll tell me expected 2 input names, but here it'll tell me like the signature, so it'll tell, okay, I've got a number and the number of bytes. So I can't use the number of bytes directly, it has to be on the stack already. So yeah, we can just yeah, we can maybe copy this. And then I can encode the wallet value of n bytes. So this will work, at least up until here. Here. Yeah, this obviously should be 4, but we can already see here. Yes. So if we look at 11, this is encoded as B in hexadecimal. And here we got basically B as the first byte and 0 as the second byte. So if I were to increase this to 4, then we just get more 0 bytes. Yeah, here. And you can see byte array have these buttons A and B. Those can be used to compare. So these don't, but here you can like diff different byte arrays. Let's try that out. But let's first cat the two things. So we can do this to figure out what's on the stack. So here it says payment amount. Oh yeah, maybe payment amount isn't the right word for this variable here. So we got payment amount here. And we can, yeah, just for fun, let's use __. This will just say, okay, I don't care about what name is here. It'll just work. So here it just swapped payment amount with whatever is on top, and then payment amount gets like moved on the top. And then we can do the same thing here. But if I save this, this obviously will fail, because now we got payment amount on the stack top. So wallet value, 4 bytes little endian, and here again 4 bytes little endian. And once that compiles, we've got these two mofos here. Okay. And now we can cat them, opcat. Concatenate, that means we just move them after each other. We just put one string that's basically the two concatenated. I don't know if there's a different word for that. And we've got this thing here. And now if we press A, we can already inspect the thing. This down here, and basically this is the byte array, and these are the two parts which it is made out of. So this is the first part, which is this one here, and this is the second part, which is this one here. So for these small things, these don't really make sense, but for like large pre-images which have like 10 different parts, and then one of those parts is a hash of a large part, and again one of those hashed parts is another hash, like 3 nested layers, and that's like normal part. Then you can inspect that very easily. You just like open it like this. Yeah, it's a bit fiddly with the tooltip, but maybe there's a way around that. Okay, cool. Any questions on that? Not yet. Okay. So yeah, let's hash that for fun. I'm not sure if combination is the right word, but let's stick with that for now. So we'll use this hashing algorithm. There are different hashing algorithms. So for example, this one is just this one twice. This one is first this one and then wrap ND. This one is, I think, broken already, but who cares? Yeah, so this will hash. Let's close this one. Yeah, and now we basically got the hash from this, and we can inspect it down here. And now we know, okay, that's the hash. It doesn't have a name, but we know the function it got applied to, and we know the pre-image, which is combination variable, and we know what it's made out of. And this actually is really helpful for doing some more relevant stuff. Okay, but let's do actually something useful. See. Let me just retweet this thing. Okay. Cool. Let's continue. So now we actually want to create a NFT. Like we want to create an NFT contract. Yeah, for that I think it would be best if we just installed what's it called? Electron Cache. There we can just but the SLP edition, obviously. SLP edition, here it is. Let me get some water. And this one, I think. Yeah. Oh man, that's a big thing. Oh no, the internet is just sluggish as hell. What is going on? It's probably due to the live stream. Sorry about that. Okay. Yeah. But the way let's have a look at this SLP specification. SLP specification. Does it show up? Yeah, there it goes. So yeah, let's start with the ordinary token type. And there, if we go to Genesis, we see like there's a whole bunch of different attributes, and those will also be present in like normal in like NFT tokens. So these are fungible tokens, and we want to create non-fungible tokens. Hey, what's up? Nice seeing you in the chat. And what we want to create is a number token. So a token that says like, okay, I'm this number and I am completely unique. And the smart contract will ensure that the number is actually unique, which is a bit tricky to do like on scale, but okay, it's reestablished. So I'll import byte array and pop key. So the public key is this can be basically any public key we want. So this doesn't have to be, this can basically be any random or known or unknown, like yeah, this is basically anyone can spend, but we put some additional constraints in that. And it will be clear in a sec what that means. So yeah, so now we got a signature and a public key, and we now also get a transaction pre-image. Oh, byte array. Oh, without the, oops. Oh, thank you. Another donation. And if we hash that one, no, do we have to? Yeah, if we have to hash that one, we get a SHA hash of that, and we can use that to create to run it against the sig check. So basically what we want to do is we want to run check sig against covenant pk and covenant sig. Check sig verify. Another donation. Okay, this. Oh wait, I don't know how much that is. That's a very low amount. Thank you. And check sig verify, and also check data sig verify. So we want to do the covenant pk, and then basically we want to, this is invalid, but this is what we want to do. Transaction pre-image and the covenant sig. So yeah, this obviously doesn't work, but if we run those two, we know that the pre-image will be a valid, like this will be the actual pre-image. Wait, but here we also need, I always forget about this one. We also need to cat the sig hash flags, which we can finally put into the params. So sig hash flags. Yeah, params dot. There they are, sig hash flags. Wait, already got it. Okay, so this obviously doesn't work yet, but we can make it work. And we also want to keep the pre-image around. If we hash this, so let me go like this. Okay. Yeah, we should also start getting propped, because yeah, that's a given. But the signature will be like generated in a different place, and the transaction pre-image will be created by Bitcoin Cash Crate. So here we just need to provide covenant pk, covenant sig, and transaction pre-image. And as signatures, now instead of the unit type, we will have a byte array. So now we will have like a single signature. And now we have to have a good placeholder signature. And a byte array is basically like a vector, but it keeps track of, like it has a name. For example, here, placeholder sig. And yeah, and some data. And for this we can use, we will use the maximum. So we won't use Schnorr here. Max signature size. It will just create a vector with zeros. I think this is 75 times. Yeah, and the cache flags will be yeah, let's also get the params. Oops. Yeah, this way we can all access the parameters from the signatory. Okay, self.params. Params and the cache flags. So what we need to provide are these three things. Public key we get from the signatory. We need to clone this, as this is just a reference and we can't get it out. But the 6, we can actually rename that to sig because that's more accurate. This we already get. And the transaction preimage we also get. Yeah, I think we can actually use transaction. Let's use transaction preimage here. So here, you can see this is a list of transaction preimages because it will create one preimage for every Zcash flag. So if we want to use different Zcash flags, this would have multiple. But here we can just use, oops. We can just use this one. Transaction preimages. I'm such a boomer. 0 and clone. Yeah. And at least this file compiles. But this one obviously doesn't because we need to provide some data. For that we need to sign stuff. And this is separated because like possibly people want to use a whatever. Possibly people want to use their own signing library. So this is in a different crate, which is here Bitcoin Cash elliptic curve cryptography. And then we can use Bitcoin Cash ECC init ECC, which will make things easy, which gives us an easy way to sign stuff. ECC. Okay, let's create a private key, covenant private key, or the secret key, and this will be just I don't know, 32 times. This is a very bad secret key, but this is all we got. Then covenant, then let's derive the public key for that. Can use ECC, derive pub key, I think. Is it that? No. Oh yeah, we need to import. I think we need to import like this. Yeah, this looks better. Okay, and then we need to supply the private key. Covenants SK as a reference. Okay, looks good. Now we got the public key, and here we need Zcash flags. So Zcash flags, and here we'll just use the default Zcash flags. So this basically means everything that could be signed will be signed. So this is the most rich option. So if you want to assign partial transactions, you can use anyone can pay. This is what WinArmani is doing all the time. But yeah, we don't, like, usually default, which is basically 0x for 1 in hex. But yeah. Okay. Yeah, let's move those parameters out so we can clone them. And also derive clone. So this means we can clone this thing later. Yeah, so I'm just basically plugging all the stuff in we need to have. Covenant PK. I'm not sure if we need to clone that, but let's see. Did I take this by reference here? No, whatever. Okay. Oh, yeah, this should be PK, not SK. And we can do. Yeah, let's clone this too. I think it'll be optimized. Okay, and now here it says I actually want a byte array to be signed. For that we need to know what we want to sign. Luckily the unsigned transaction gives us the thing we need to sign. So it's pre-images, and there it gives us for every input all the pre-images it creates. Pre-images, whatever. So yeah, so this is for the first input, all the pre-images, and we just need a single pre-image because we just have one sig hash. So this is the one we will get. Yeah, vector of transaction pre-image, and now this is a single pre-image. It for some reason isn't able to derive that, but it could be worse. And then we create the signature. For that we use ECC and sign. There we get the secret key. I mean, for signing you always need a secret key. And the message array, which has to be hashed, by the way. So we need to do this here. Digest pre-image, and then 2-byte array, I think it is. And the last thing, yeah, that's it. Okay. And question mark, because this can fail. And we also need to import hashed trait, which allows us to use digest. Okay, let's format this. Definitely not used to Windows keyboards. Okay, and the 6 is here, signature. Oh yeah, So all of these need to be public, but that's okay. Yeah, okay, not finally compiled. And we should see, yeah, updated. Okay, now here it'll hash the pre-image. This is the pre-image hash. Wait, not this, that's the old stuff. No, this is the pre-image hash. And we can see there's a lot of stuff in there. So it's already correctly named. So you don't have to even specify the names. We got the end version, and let's compare this with here. So this is the specification of the pre-image. So we got the version 4 bytes, we get the hash pref outs 32 bytes. We've got the hash sequence, also 32 bytes. The script code, which is variable length. Yeah, this looks really weird. Oh, another donation. Thank you. Thank you. Why is this so weird? Script code. Anyway, yeah, we'll figure it out. What is this? 0C. Anyway, okay. Then we got the value. I think this is not correctly named. What should be here? Ah, this is odd point. This is incorrectly named. Oh gosh. Okay, I need to fix this later. So this is the actual script code. It's unnamed. We just got 2 bytes. We just got AH, which if we look it up, maybe we'll see. No, too bad. But if we control click, yeah, oh yeah, A8, A8. So here we've got AH, and the 1 is the length of the script. So this says, okay, and this thing is just a single byte, which is for the 1. Then the end sequence, this one, the hash outputs, which here is the empty string because we don't have any outputs, which I mean is just the way it is. And the log time is 0, and the sig hash is like this thing here, which means basically everything is hashed. Yeah, it's a bit colorful, and the colors are chosen with a pretty weird algorithm, but it usually works out fine. So what was important here is that, like, if you if there is like this thing is made out of this thing, which is made out of this thing, then it should line up like this. So if there's some stuff here, then on top it should have the correct name. It should be lined up with the bytes. Okay. Okay, so let's check this pre-image, because currently this could be anything. This could be whatever. So I think, yeah, let's just do it naively. Let's just duplicate the pre-image. Selection pre-image. And then, yeah, we can directly see how it looks like. We've got the hashed pre-image and these two. Now, I don't know, let's do, it's probably not the most efficient way, but let's just do it. We can do toSwap. And here I usually do the things I want to get on top, which is PK and covenant sig. Or should we? Maybe we should do 2 over. I don't know. Let's not be too efficient now. Oops, this won't work. I wanted this to be this way. So yeah, so this will basically excavate those 2 on the top. Yeah, no, they are on top. So if it's blue, it means it's moved, and if it's a bit fainter, it means like this is more moved indirectly. So now we got those 2 on top, but they are in the wrong order. So let's oh wait, we can actually, if we do rot, no, let's swap those 2. Oops, how can I swap? I don't know. Yeah, we swap the 2 inputs, and then we can get them in the right order. Oop. Yep. So now we got sig and pk, and if we do to dub op to duplicate, and here we got the covenant sig and the covenant pk, then we got those two in the stack, and then we can already do the, oh no, wait, we need to concatenate the sig hash first. So let's let's do that one back. I always forget about the sig hash, it was really annoying, but secure. Covenant pk, and we have got the duplicate, so we can just covenant sig flagged, I don't know. So but we have to put the sig hash flag on there, and there we can use like Rust syntax. Sig hash flags. So we can just like use vector and then push the sig hash flags, which currently is just a single byte, and I think it will always be just a single byte. And now we can access the params and the sig hash flags, and I think it's bits and then SUH. Let's make this a bit bigger. And opcat, and now we can concatenate the covenant sig with the sig hash flags. Okay, and let's see what we got on the stack. If it may. Okay, yeah, as you can see, it starts to get a bit larger, but that's okay. Now we got the, so what's the difference? So here we've got 70 bytes of a signature, and here we got 71 bytes. And yeah, let's actually compare those. This will be A, and this will be B, and now we can show the difference. As you can see, the only difference are these bytes here, and we can actually see that those are the sig hash flags, those are the covenant. Oh, and we see a thing it's signed, but yeah, let's keep that aside for now. And this here is required for check sig verify, but for check data sig verify we want this one here, so we keep both. We've got this one and this one around. So, but check sig verify wants it in a different order than I did here, so this is incorrect. To do check sig verify, no, not check data sig verify, nope, that I didn't want. Just check sig verify. So we need to swap them again. So the covenant pk is on top, public key is on top. Covenant sig flagged, and then the covenant sig flag is on the bottom. Covenant pk is on top. And let's see if that works. No, wait, we also need to, oh yeah. And we can see a script executed without errors. So this totally works fine. Kuru. And now we just need to check this thing here. But I think it's in a bit weird order. So this needs to be put here. Yeah, I mean, we can put more thought, like this is basically the magic or the wizardry behind scripts, like figuring out how you can do this stuff without like too many of these operations here. Yeah, I think it's not very smart to like start out with duplicating here, but whatever. So we do a rot, op rot. So we get the transaction pre-image on top. We can check this one. So this basically moves this one over here and these two over in the back. And after that, we'll do a swap. Swap. And yeah, so the covenant sig is on top. And transaction pre-image is one behind. We can do check data sig verify with the covenant PK on the bottom, the transaction pre-image hash, and the covenant sig. Wait, other way around. Yeah, we just did all this hard work for getting it in this order. So the covenant PK. Great. Let me see if there's one viewer. It's a bit fewer. Anyway. Okay, yeah, I think I messed up. This should be... oh yeah, this is in the wrong order. Yeah, so we need to swap before we do rot. I mean, this looks really inefficient, but this is fine for now. Covenant PK, covenant sig. I usually spend a bit more on figuring out that this works fine. PK. Now we can do check data sig. Now we can see it's in the right order. So check data sig verify. First wants the signature, which is what we got. Then we want a message, and then we want the public key. Yeah. Covenant sig. Yeah, and here we can see that it executed successfully. Okay. Here. So script executed without errors. So if you were to put this in a normal transaction, then it will fail, I think, at least before that, because it needs to have a clean stack with just a single entry, which isn't the stack here. Yeah, which isn't the case here. Okay, cool. Now we just got the pre-image on the top of the stack. And now we can disassemble this thing. Which parts do we need? I think we only need the outputs. Not the script code, not anything, just the outputs, yeah. So we will, yeah, just use size. Yeah, okay. So for that, I usually measure the size of the script code and then cat, like before creating the thing, and then cut here. But we don't need to do that now. It's like we're already not very efficient, so that's fine. Yeah, so let's get this size. Wait. Pre-image size, which is op size of selection pre-image. Which currently is 171, and that is totally fine. Now we can like subtract the starting point we want to have from the back, basically. So we want these 4 things. Let like number bytes back or so, like that, and we can do curly braces. This will just be an expression, so this doesn't change a lot. It's just to be nice. Yeah, and I usually copy paste when I do pre-image stuff. I just copy paste the part that I'm talking about. So we've got 32 bytes here, we've got 4 bytes here, and we got 4 bytes here. Then we do OP split. Oh no, wait, first OP sub. This will be pre-image size and number of bytes back. Let split index. So it'll split at this index, and we can do OP split to actually perform the split transaction pre-image split index, and let's just see what comes out of that. So we got 2 arrays. This thing here, which has 40 bytes, which coincidentally is this amount, so that's great. And we got this part here, which we don't really care about. I mean, not in this covenant. We could, like, a very, very important part is the script code and the value. These two are very, very useful. The other few, not really, but. Okay, so we got that out. And we can put pre-image. I usually do pre-image parts 1 to 7. The other is pre-image parts 8 to 10. Yeah. And then if we want to get the hash outputs, we just split at 32 bytes. First, let's remove the pre-image parts 1 to 7 because we don't need those. Nip will pnip. This will remove the second to top stack item. So split takes a byte array and a split index, and it splits at the index, and we'll push 2 items, first this part here and then this part, and now we just remove the first part because we don't need it. And then we will get hash outputs and like the remainder, which is pre-image parts 9 to 10. Yeah, and those should be at size hash outputs, which is 32. Now we can do OP split with the pre-image parts 8 to 10. Size hash outputs. And we can OP drop. Oh yeah, we can see what happened. hash outputs, and we can actually inspect those if those look legit. So hash outputs, this says it's like hash, it comes from like double hashing, which is correct, and we actually can expand the thing, and we see, okay, it got a empty, it's based on like the empty string 0 bytes, because we don't have any outputs. We can enforce those later. Yeah, so let's clean up the remaining parts. And now we just got the hash outputs. So now we can basically enforce which outputs we want to have. And here we just want one output that'll be the SLP genesis, and one output that'll be the recipient of the token. And we get the token name as, I think the best way would be to be the first push operation here. Yeah, I mean, that's a bit late to do now, but we can. It's usually very bad if you like have to change the stack afterwards. But yeah, how can we do this? Yeah, let's do it properly. Let's do it well, like we should do it. Okay, so the idea is we get we build the transaction with this function, but then we we split off the first part, and then just the remainder will be basically the part which we will use later in a previous script, which will then say, okay, I've now generated the number via some algorithm and process. Now create the token, and for that it'll basically do some meta programming kind of stuff, where it'll concatenate, basically will assemble this thing in script, but this part here will be like fixed. So everything here will be fixed except for the first push operation, and then it'll only be able to create a single transaction, a single token type. So let's try that. We have to stop this. Let token name. So yeah, this comes from the params. Let's do here token name, and this can be just should be. Let's do a vector. It doesn't really have to be a binary. So yeah, we push the token name. So here this could be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. For example, that's the number you re-registered to Mac. And yeah, let's wait until this is compiled. Yeah, which is this thing here. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Or in like ASCII, this is this one here. And now we can actually be a bit more sneaky. So we can do 2 over. To get covenant PK and covenant sig. And then we can do this part here, unchanged, I think. Oh, 2 over. Let's do the placeholders. Yeah, looks really good. Without errors, sig flagged, PK. And now we just have to take care of this part here. I think the best way would be to check this part at the very end. So first check this thing here. Yeah, so we keep that in the queue, and then we get the pre-image and disassemble it here. So do OP over transaction pre-image. So basically get the pre-image on top and disassemble it. So remove that one. Wait for it to be finished. Okay, there it is. That's not slow actually. Yeah, and now we still got the hash outputs and the token name. So another thing we will want to have is basically the recipient address. It's basically the guy who purchased the token, and we also have to put that here. So we can't use 2 over anymore, except if we switch things around. Yeah, this should also be here. Let token name and token recipient. Do we have any questions? No. Yeah, so this will be an address, of course, but we only need the hash part of that, and we'll just assume, yeah, we'll just assume that it's paid to public key hash. Oh, do we? Oh no, let's make it recipient public key hash. Let's make it this way. And then we get a hash 160. And then that's great. Yeah, and if we move that thing down here, then it should still be. Just that we got the wrong thing on top. Okay, so let's comment this one out. Yeah, I'll obviously need to specify the recipient here, which will just be like a random string again. Yeah, let's just put like 1 20 times. Which is definitely not a valid hash, but it'll work. Yeah. Yeah, it'll have this nice gray. So it's like, okay, this thing is the copy of this thing here. Okay, so let's assemble a the output from this one. So we want one OP return with one quantity, and it's going to be a SLP NFT1 token, a child token. Yeah, but let's do a fungible token for simplicity now, and then we can just change the thing, the type. Bitcoin Cash SLP. So for that you can import SLP, because I split it into different package. So like if people don't do SLP, they don't have like these dependencies that they don't need. Do we really have to restart this thing? Whatever. I'll just do it. Okay, whatever. Yeah, I don't really feel like doing that part. I mean, the rest should be pretty, like, it should just be the same stuff over and over again. Yeah, but I think the best way forward from here is to like have a look at the opcodes, how they work. You can like currently the rest and yeah, there it is. Yeah, you get nice helpful texts here. I think the best source would be docs rs and then Bitcoin Cash. And then if you go to opcode, where is it? You get every single opcode and always a short description. For example, verify. Stuff like that. Yeah, if you just like go through that, it'll make things much easier. You can also go to reference.cache. Here, operation codes. Where they are described as well. Yep, and then you can make all sorts of things. Cool. Yeah, I hope this was helpful, and yeah, tell me if you want something like this again, because yeah, what we can do is like print. So basically, if you were to like do this, and then do this, I think no, serialize unwrap, yeah, and then depend on hex. I think it's 0.4. Just like this, encode. Let me add that signature. Then it'll print out the transaction hex, and we can actually, I mean, you could try to broadcast this thing, but it obviously would fail. I usually just use Bitcoin Cash transaction broadcast. Yeah, I think this one works. And this one doesn't really tell me what's wrong. Cache. Okay, that's even worse. Yeah, there used to be a really nice website for that. Let's see. Interesting. Yeah, usually it shows like a better message than that, but yeah. Yeah, and if you were to create a valid transaction, you could put this into a function basically, and then compile it with like JNI, WebAssembly, or just normal plain C API, C API, and then you could use it in all sorts of environments, like in C++ or on Swift. I was able to get it to work on Swift. I mean, Open Objective-C, which can then be interfaced by Swift. Yeah, and then any platform you want can use this smart contract stuff. Alright, I hope this was helpful. Gotta end the stream here. I'm a bit, I don't know, talking this long is a bit exhausting. But yeah, thanks so much for all the donations, and tell me if you liked it, and see ya.